Next, I will show how to apply the goodness of fit procedure to test a statistical claim about the distribution of a categorical variable. Consider the following example. The table shows the distribution of emergency room visits across the days of the week in a random sample of 434 visits at a random local hospital in a large city. Use 10% significance level to test the claim that the emergency room visits are evenly distributed across the days of the week. Now, let's identify the statistical claim that needs to be tested. The claim is that the emergency room visits are evenly distributed across the days of the week. But what exactly does it mean to be evenly or uniformly distributed? If that was true, we would expect all days to have the same number of visits. What would that number be in our case? The total is 434, and to have a total of 434 while uniformly distributed would require a 62 visits per day. So we expect the following outcomes. This is called the expected distribution, and what we obtain from the sample is called the observed distribution. Before we begin the goodness of fit procedure, let's check if all necessary assumptions are satisfied. The sample must be assumed simple random. If not, then the results of the test are invalid. All expected frequencies must be 1 or greater, and at most 20% of the expected frequencies are allowed to be less than 5. We will use the following template to perform the hypothesis testing. In step 1, we will set up the hypothesis. In step 2, we will identify the significance level. In step 3, we will find the test statistic using the formula. In step 4, we will perform either the critical value approach or p-value approach to test the claim. In step 5, we will draw the conclusion, and finally in step 6, we will interpret the results. The null and alternative hypotheses are always the same in a goodness of fit test. The null hypothesis is that the variable follows a specific distribution, and the alternative hypothesis is that the variable doesn't follow the specific distribution. In our case, the variable is the days in which an ER was visited, and the type of distribution is uniform. So the null hypothesis is that the number of visits to ER is uniformly distributed, and the alternative hypothesis is that the number of visits is not uniformly distributed. The goodness of fit test is always right tail. Step 1 is complete. The significance level can always be found in the text of the problem. In our case, it is 10%. Step 2 is complete. The test statistic will be computed using the process rather than a formula. In a goodness of fit test, the test statistic represents a measure of how far apart is our observation from the expectation. The larger the test statistic, the further apart they are, and therefore the stronger evidence it is against the null hypothesis. To compute the test statistic, we find the difference between the observed and expected values first. Then we square the difference so that the negative difference is contributing to the total difference. To standardize this measure, we divide by the expected values. And finally, we obtain the test statistic chi-square 0 by adding everything together. The table summarizes all the computations of the test statistic chi-square 0. This measure follows the chi-square distribution with 6 degrees of freedom, which is the number of categories 7 minus 1. Step 3 is complete. Next, we will test the hypothesis using two different approaches, the critical value and the p-value. In the critical value approach, we construct the rejection region. In this approach, we need to know the significance level alpha and the type of the test. We draw the rejection region under the chi-square probability density curve with 6 degrees of freedom according to the type of the test. So right tail test will have the rejection region in the right tail. The region must have the area equal to the significance level 10%. So the left boundary of the region is the critical value, chi-square 0.10, which is equal to 10.645. So the entire region can be described as all the values to the right of 10.645. In p-value approach, we compute the p-value. In this approach, we need to know the test statistic and the type of the test. We find the p-value using the chi-square probability density curve with 6 degrees of freedom, according to the type of the test. So in a right-tailed test, the p-value is the area to the right of the test statistic. Symbolically, it can be expressed as the probability of chi-square being greater than 24.26, which is equal to 0.0005, which is effectively 0. Next, we're going to decide whether to reject or not reject the null hypothesis. In the critical value approach, we must check whether the test statistic is in the rejection region or not. Our test statistic is 24.26, and it is to the right of the critical value 10.645. Thus, it is in the rejection region. In the p-value approach, we must check whether the p-value is less than the significance level alpha. Our p-value is effectively 0, and it is less than alpha. Both tests suggest that we do reject the null hypothesis in favor of the alternative. Next, we are going to interpret the results. Interpretation. Under 10% significance level, we do have sufficient evidence to suggest that the emergency room visits are not uniformly distributed throughout the week. The hypothesis test is complete. Does this mean that the visits are more likely to occur on the weekends? No, the purpose of the test is only to check whether it follows a uniform distribution or not. Any other claim would need to be tested separately. I just showed how to apply the goodness of fit procedure to test a statistical claim about a variable following a specific distribution.